Every day, thousands of freight trains travel over Australia's 33,000 kilometers of railway, creating immense pressure on the tracks. Over time, this wear and tear can cause rail breaks, which not only delays operations but pose serious safety risk and high costs for freight companies. Our project, the Rail Break Prediction AI, aims to solve this problem by predicting the rail breaks are likely to occur before they happen, enabling preventive maintenance. Our primary users are maintenance engineers who rely on these predictions to schedule repairs and prevent disruptions. However, there are also other users involved. Data analysts will use this software to test different models and improve prediction accuracy, while project managers may use insights from the software to assess maintenance effectiveness and optimize budgets. So our software serves multiple users, each with different goals but work towards the shared objective of safer, more efficient railway operations.
Our rail break prediction project follows a structured software architecture, starting with dataset combination from key tables, followed by data cleaning to address inconsistencies like outliers and missing values. Next, feature engineering scales and refines data, and feature selection narrows down the most relevant variables for model training. The final process data splits into training and test sets, ensuring balanced evaluation. Model development includes training and hyperparameter tuning to enhance accuracy. Inference creation uses the model for predictions, with submissions made to the Insight Factory leaderboard. This pipeline ensures a seamless workflow from raw data to actionable predictions. We leverage concurrent model development by establishing multiple pipelines for individual experimentation within the Insight Factory Databricks platform. We use modular notebooks that allow easy adjustments to hyperparameters through metadata tabs, ensuring flexibility. This approach streamlined the process of refining models and optimizing performance. It facilitated seamless collaboration and efficient iterations, resulting in a smooth workflow that led to high-quality predictive insights and the successful leaderboard submissions.
Next, I will talk about the structure for the data processing pipeline. The data pre-processing was broken down into four main stages: data combination, data cleaning, feature engineering, and feature selection, each contributing to preparing the data for model training. In data combination, the rail break location, tonnage, wagon, and train tables are loaded and joined on a primary key to create a unified dataset, which is then saved for the next stage. Moving to data cleaning, we load the combined data and then remove outliers and handle missing values to ensure data quality. This clean data is then saved for further processing. In feature engineering, we enhance the clean data by transforming the temporal features to be represented as sine waves of different frequencies for better model understanding, add an anomaly label by training an unsupervised isolation forest, and scale the data for better model predictions. This engineered data is then saved to the catalog. Finally, in feature selection, we remove irrelevant features by finding highly correlated features and applying best intuition about how to proceed. Apply dimensionality reduction via principal component analysis, and balance for class labels using SMOTE to address the class disparity. The final data is then saved ready for model training. Together, these steps ensure a comprehensive approach to data preparation, creating a robust foundation for training accurate and effective models.
Hi everyone, this is Feng Yuan here. I will be introducing you model creation and submission to tasks. So in this phase, we consist of three steps. The first one is model creation, the second one is inference submission, and the last one is submission to the leaderboard. So for the model creation, just do a brief one. So it's introduce algorithm selections, choosing an operator algorithm to suit our dataset and prediction goals, and then we use hyperparameter training, like experimenting and optimizing to improve the overall performance. The final goal is a model that maximizing the F1 positive score. Well, speaking of the inference submission, once we have the model, so we will be using the existing model to predict the unseen data and output predictions into DF result. Well, the DF result is an array of booleans of 0 and 1s, where 1 indicates there is a real break, and 0 indicates it has not predicted any break. Well, the purpose is just to provide a structured output to evaluate the model predictions. So the final one is submission to the leaderboard. It's upload the DF result to the leaderboard. So it calls internal function to run the evaluate predictions using the F1 score. So the benefits, like there's feedback mechanisms. We got the immediate performance feedbacks as allows for iterative improvements. and also have a benchmark against previous submissions to track progress.
Over the semester, our group made significant progress each sprint towards our goal of creating an accurate predictive model. For Story 1, we collaboratively identified and explored 5 techniques for feature engineering, feature selection, and imbalanced dataset methods. We collated our findings in this Google document, which we shared with the client. For Story 2, we went ahead and implemented 3 of each of the feature engineering, feature selection, and imbalanced dataset methods in collaborative notebooks for each domain. We performed some basic testing with these techniques and reported our progress to the client during the client retrospective. This sprint, we also saw the submission of our first model to the Insight Factory leaderboard, which was a slight modification to the random forest classifier blueprint provided by the Insight Factory, achieving a best score of 3.65%. During Sprint 3, we created the first version of our custom production line, which facilitated collaborative development and separation of data processing tasks. These data processing tasks offered multiple techniques for each of the feature engineering, feature selection, and imbalanced dataset tasks, all of which had tunable hyperparameters that were adjustable from within the Insight Factory via the Tasks Metadata tab to facilitate rapid experimentation. These data processing tasks fed into our 3 distinct and tunable models, which we spent time trying to fine-tune, enabling us to increase our F1 score by 43.44%. To keep track of our experimentation, we began implementing various documentation methods to report what combination of techniques were working so far. During Sprint 4, we continued our experimentation by revising our custom production line to enable more group members to experiment with feature selection, feature engineering, and imbalanced dataset methods. With this increased experimentation, we also revised our documentation process, opting for a new Google Sheet which automatically sorted models based on their F1 score, enabling users to quickly and easily see what techniques were working effectively. This helped bring up our F1 score again, achieving a score of 49.44% in Sprint 4. During the sprint, our group also began researching explainability AI techniques, collating our findings in this document, which we reported to the client during our retrospective. During the final sprint, we evaluated the training set using SHAP to look at feature importance and gave one last push in an attempt to optimize our F1 score, leading to 40 entries in total within our model documentation. Additional techniques such as converting a recording date to seconds were incorporated, along with binary search approach for finding the optimal hyperparameter values. This ultimately led us to bringing our F1 score up again to a final result of 49.48%. While it was not the F1 score we had hoped for, our group made significant strides forward, advancing our understanding of a range of machine learning techniques, implementing multiple documentation processes, and conducting a lot of experimentation.
The typical usage scenario for the rail brake prediction AI would involve the maintenance engineer at the Australian Rail Track Corporation logging into the platform for going through predictive analytics regarding the risks of rail brakes at the start of his day. The software identifies the high-risk sections of the railway network by taking the latest sensor data combined with historical records to pinpoint areas that are likely to show cases of rail failures. With this, the system points out a piece of the track, quite remote but very likely to fail due to a compounding effect of increased tonnage, poor weather conditions, and the historical wear and tear pattern. The engineer can utilize the features of the software to dig deeper into risk factors at work and therefore may reveal that unusually high tonnage during the past week is the main contributor. Armed with this critical information, the engineer can take proactive action by dispatching a maintenance team to inspect and reinforce the vulnerable section. The preventive action will impede the possibility of rail breakage, avoid costly operational delays, and ensure that operation freight is sustained with safety. This example, if taken in isolation, provides good insight into how rail prediction AI has taken difficult data and through processing turned it into usable insights that enable engineers to allocate resources more appropriately and make sure the railway network is safer and more reliable. Unfortunately, due to no further access with the application, I cannot show this use case in action.
In Sprint 1, from the user's perspective, this research sets up a stable foundation for developing a robust predictive model. By exploring various methods and techniques during this sprint, the software engineer ensures that the final product is built upon the best possible strategies. Here is the foundational research performed and documented during the sprint as shown in Figure 7.1. In Sprint 2, by implementing and testing feature engineering methods, feature selection methods, and machine learning techniques to approach an imbalanced dataset, the software now moves from theory that was built upon Sprint 1 to practice. Users benefit from the initial version of the predictive model because now it starts providing some insights into the problem. Here are the feature engineering, feature selection, and balancing dataset techniques that were built off from Sprint 1, putting into action as shown in Figure 7.2. In Sprint 3, trying out models and fine-tuning hyperparameter and additional techniques resulting in improvement on prediction on the F1 score. Improving the F1 score means enhancing the model's accuracy in predicting rail brakes, balancing both precision and recall. Users get more reliable predictions, reducing false alarms and misdetections. Here are the hyperparameters fine-tuning and some additional techniques like PCA that were implemented in order to improve the F1 score as shown in figure 7.3. In Sprint 4, model explainability allows users to understand why the software makes certain predictions. This transparency builds trust and enables users to validate and interpret the results effectively. Here are more documentations on Sprint 4 relating to XAI as shown in figure 7.4. In Sprint 5, identifying key features gives users insight into primary cause of rail brakes. Achieving an F1 score of over 70% ensures high predictive accuracy and will be more effective prevention strategies. Again, users will now get more reliable predictions, reducing even more false alarms and misdetections. Here are our final implementation of the software architecture and some of the key features we identified as shown in figure 7.5.
To improve the practical application of the project, short-term and long-term goals could be implemented. Short-term goals focus on enhancing the accuracy and robustness of the existing machine learning model. Currently, the development pipeline lacks an independent testing framework for modules, making it difficult to isolate and troubleshoot individual components without affecting the entire production pipeline. Our proposed solution is to develop a modular testing environment using framework like PyTest. This will allow for unit testing of each module independently. Furthermore, Databricks' high computational needs slow the development cycle, especially during parallel model training and testing. We could introduce caching mechanisms for intermediate data processing to reduce redundant computations. Using Databricks Data Lake could help efficiently manage data storage and retrieval, particularly when processing large datasets. There are also long-term goals that aim to make the software scalable and autonomous, integrating with ARTC's operational systems. As of now, our model lacks a pipeline for automating retraining as new data becomes available, requiring manual intervention to update the model. We could build an automated retraining pipeline within the Insight Factory platform that triggers when new data is added to the database. This automated pipeline would retrain the model, validate the updated performance, and deploy the new model version if it meets the F1 quality standards. Furthermore, the project currently also lacks a historical data dashboard that business users can use to analyze long-term trends and patterns. We could implement an analytics dashboard using tools like Power BI or Tableau, connected to the Databricks Data Lake, where stakeholders can view historical data on rail brake predictions and track conditions using the explainability AI model results. This dashboard could include trend analysis, risk visualization, and insights on factors contributing to rail failures over time. By planning for these future enhancements, the project can grow to provide actionable data-driven insights that contribute to Australia's rail safety and efficiency.